We are a consortium of Earth observation specialists working for the European Space Agency.
The framework in which we operate is twofold. The first guiding principle is the United Nations Sustainable Development Goal 11. Make cities and human settlements inclusive, safe, resilient and sustainable. The second framework is the Project Implementation Strategy in international financing institutions like the World Bank and other development banks.
Our aim is to extend and improve the use of satellite data for the monitoring of indicators in order to reach Sustainable Development Goal number 11. We also want to facilitate international development work in a globally consistent manner by using Earth observation data and methods.
We have covered 32 cities around the globe with a total of more than 510 products and 11,000 square kilometers mapped. Our basic products comprise status and evolution of urban extent, as well as land use and land cover and its change over time. More specifically, targeted maps include slum maps, maps of open and green spaces, building footprints and heights, infrastructure, as well as hazard and risk maps. Based on these maps, we generate spatial analytics and the before-mentioned indicators for SDG 11.
These tools are very much relevant because they provide evidence.
In general, the preparations of bank operations take several years, but in these cases, it only took around 6 to 8 months for the preparation, thanks to the whole analytics, maps, and data evidences. The best part is that it was helpful to communicate with various stakeholders on the ground.
I would like to give the floor to Tomas, the first presenter.
Okay, thanks Manuela, and good morning or good afternoon whenever you are attending our webinar. So as mentioned by Manuela in the introduction, this talk will be more about the technical details or some technical specification of the products, then about the application of the data, because we thought that it would be a good if you have some kind of insight how these data are done, so you can also better understand what is the contents of the data and subsequently how you can use the data the best way. So I started my part with the slide providing the overview of our portfolio. And I think those of you who have participated already on previous seminars, you already know this picture. I will just pick up the word standard products because I just want to give you some clue what we mean by that and what makes it different from kind of one-time ad hoc production and the standard product. So in our product portfolio, the products are based on the specific use requirements, which means they are tailored to some urban sustainable development support. All the products are harmonized in specification, so there are some logical links. And also there is a standardized methodology how they are done. So even they are produced by the different partners, they share the methodology, so you can be sure you get the same product. And importantly, we also have quite a stringent quality control procedures, and all of these is quite well and transparent documented. So that's what we consider, let's say, the standard product, and that's what I think it's also important for you to understand how you can trust the product. So I will start with my part of the presentation, but before, just if you would need any more information about any products from our portfolio, you can also go to our website and use the link, which is in the presentation, where you find some service portfolio brochure, which you can find more information. So for the sake of this presentations, we divided our product portfolio to the 3 groups. As it was mentioned by Manuela, I will talk about the urban structure group, and then the other groups will be commented by Jan and by Manuela. So let's concentrate on the urban structure group, which is a group of the products where we provide the information about the urban structure in space and also about the evolution both in space and time. We provide a number of products, as you see, on various scales, and also this is somehow reflected in a different specification with the various thematic details, and also somehow in a base EO data which we use. That's also something what I would like to. So why we have a range of these specifications? First, from the user point of view, obviously there are different requirements and needs on a different scale. And as I already mentioned, also there is this technical aspect. So we also produce the products with a different resolution on a different scale, and also from the point of efficiency, a bit cost-related aspects which are due to the different EO data used, and also the complexity of the information extraction for the different products. So on the bottom line, you see kind of orientation for you where the different products place in this global local range. So I will start with before I will start with the global product, I just example what I mean this range and the link to the EO data which we use. Just for your understanding, this is, for example, the high resolution image which we use usually for the global products. And this is example of the very high resolution image which we use for the detailed local products. So as you see, of course, the number of let's say information and the detail of information is different, and that's also reflected in the specification. But it cannot be said that, for example, just the very high resolution is the best data for our product, because if you, for example, are interested in a long-term monitoring, then the high resolution data provides you, let's say, the best answer for that. Okay, so let's start with the first product from this global part. And this is the urban extent and possible change of this extent product. It's a binary information, so it's really basic information about the urban area, about the city. So where is the built-up area? Where is the non-built-up area? Sometimes you can find the name like urban footprint or settlement footprint for these kinds of products. This product is prepared by closed automatic way. Closed, of course, there still needs some intervention, some calibration, but in general, the procedure is very much automatic. We use the high resolution data, as was exemplified, and another advantage of these products is that they are based on the free and open data nowadays on the market. So that means also that from the point of rollout, it's quite easy and to do it for a large area. So this product provides the decision maker with insight into amount of built-up area and its spatial distribution. And when you have changes, of course, also about how these qualities are changing over the time. And because it's a global product, the big advantage is also that you can produce it for a large area, so it can serve you as a benchmarking tool also for cities, group of cities, even the continents. So this is just example of the urban extent product for the content. And I will continue with the imperviousness product, which in fact is close related to the urban extent. It's just additional information. So it provides you for the areas which were identified as the built-up areas. It provides you information about the imperviousness level of these areas. Sometimes you also can see the term the level of sealing. So because these are the twin products, this product is also based on the same data, and it's also produced in an automatic way. So in addition to information which we were discussing in a context of urban extent product, the imperviousness provides you also information about the density and the built-up density distribution in space. And when you have a change information, it gives you also some clue about the densification versus expansion processes for individual city or for the group cities. Again, you can benchmark on a larger area. So this is example of these two products for the company. And I would say these products start to be even more exciting, of course, if you have a temporal profiles for these products. So for example, if we move to year 2000, you see, and then 2010, then 2015, you see quite transparently how the city is expanding. You see how the density of the city is changing. And these are the information which of course are quite useful, because you can basically identify some axis of the growing of your city. You can basically say a lot about how your city is expanding, and you can compare it with some other cities. So that's about the global products. And before I will finish with this part, I just want to show you that, of course, this information can be then further analyzed. You can produce a number of statistics. This is example of, let's say, built-up share, but you can also analyze it in a time aspect. So you can compare how it's the annual rate of this increase and things like that. But before I will finish with the global product, I just would like to announce to you that there is a really exciting product coming soon, which is called World Settlement Footprint Evolution Product, which is covering even longer period than it was exemplified on Pompen. It's from 85 to 2015. So if you are interested in this kind of product, I should say this will be available globally. Please join our webinar, one of our next webinar, which are announced on the page, which was at the beginning pointed by Manuela. But it's the time to move on to the next group of the products. And the next group of the products are the urban and peri-urban land use products. This group of products are categorical products, so it means they are classified areas into standard nomenclature of the classes. These products are prepared by semi-automatic way. So the level of, let's say, automatic part very much depends how much to the land use we try to go, because of course land covers are quite easily derived from the satellite images, but more and more you go to the land use, of course you find some limitations. Just to exemplify, I think it's not difficult to discriminate built up and green, but if you want to discriminate for example, the industrial and commercial areas, or public or private parks, and of course it starts to be difficult. So these types of products are usually produced from data with 1 meter or 5 meter pixel resolution range. These are already commercial data, and it provides the decision makers, in addition to urban excellence discussed before, also the composition of the city. So which is the share of different land cover, land use categories within the city and surrounding areas. And in addition to change amount and rate from the previous product, it provides you also information about change quality. It means about the categorization of the changes, some information about land consumptions and formation flows. Using these data, you can also kind of anticipate much better the driver groups which are behind these developments. So I will quickly show you the way how these products are derived. So we obviously start with the image, which we segmenting. We use spectral, texture, and sometimes also ancillary information. On the technical side, we use both the object-oriented and also pixel approaches, and we end up with some homogeneous units, which are then classified, as I said, to the standard land cover land use classes. I will just quickly mention that these products they have a long heritage in Copernicus Urban Atlas development. So what we are trying basically is to utilize this heritage in the international level. So when you have these classes assigned, I mentioned that we also deal with the change products here. So of course you can compare the images and the assignments on the individual time steps, and you identify some potential changes, and then you use some temporal or contextual or logical rules, and you apply these in a way to obtain the standard changes, and also you assign the change flows to these changes. Again, there is a standardized nomenclature for that, and you can in this way compare the different cities which are produced by the different producers. And at the end, of course, you can analyze these data in a way similar which we discussed in the urban context. So, but you get much more, let's say, detail and insight to the internal structure of the city. So you can analyze different type of changes, different land formation, consumption patterns, which I think when you consider land as a finite source, it's very much important information to really assess how sustainable the city is developing. Because of time, I have to speed up a little bit. So we still have 2 more products from this range, so I will go quickly through. Now we are on, let's say, on this local or very detailed part of this range. And the first one is a building footprint. Building footprints can be described as kind of delineation or contour of the houses and other man-made buildings. And this is something what you commonly find, for example, in cadastre systems. But of course, there are applications, there are countries where these data are not available. So similar product for individual buildings or the block buildings can be prepared using your data. So obviously these type of products are produced on very detailed imagery. So we usually work with a sub-meter pixel resolution. We also need some ancillary information, for example, like OpenStreetMap. And the level of automation, of course, depends to the extent how smooth or how precise these contours of houses or building footprints are required. So what it provides to the decision maker, it provides you detailed information on the spatial distribution of individual buildings, or at least the building blocks. So you can count the number, size, different parameters which are important for your analysis, and you can do it in urban or peri-urban area. This is just example, so you can produce also for the building footprints, you can produce some change detection. So for example, on the right, you can see which buildings were demolished, which buildings were already there in 2009, which of the buildings, these are the green ones, were built in 2014. So this kind of time analysis or change analysis can be, of course, done also with this product. In addition, you can attach a number of additional information like roof quality, or here on the left you have a 3D information attached to building footprints. So you can then use it for a number of applications, especially in emergency area, or what we did also, you can use it for some tax estimation, for example, which is quite interesting area in a number of countries. So I will go quickly to the last product, and this is transport infrastructure. In fact, this is already a little bit bridge to Jan, who will talk about the specific products, because you can consider transport also as a specific feature in the city. But I include it in my part because we use a transport infrastructure or direct transport infrastructure also as a part of the production of these baseline products, because usually we use it for kind of skeleton to build the blocks within the city, which we then assign these categories, which I described previously. So itself, the transport infrastructure, as the names say, we provide a delineation of roads, streets, railways, network with a high level of details. The typology can be different, but it's usually a hierarchical and somehow reflects the depth and quality of the surface. It's done also on the very detailed data, usually also submeter. And we usually start with OSM data nowadays, because for a number of cities there are already some transport infrastructure data globally available, but we try to update using the data or attach some additional information like number of lanes, presence of sidewalks, something what is also then used in a next products which you will hear from Jan and from Manuela. So what these products provide to the user, it provides up-to-date information in transport infrastructure, in some standard infrastructure typology, and data can be used except the production, for example, these baseline products. As a support, it can be used in a manifold of other analyses like access to transport modeling, noise, access to green areas, and so on. So as a final, this is an example, for example, of such an update done in Denpasar, Indonesia. And this is just an example of some application which could be used. In this case, it's accessibility analysis in Dhaka, Bangladesh, where we combine the detailed information of the transport infrastructure with a detailed population density product, which will be also introduced by the Manuela. So that was, let's say, very briefly from my side about these urban structures on the different scales and these different thematic levels. And I will give the floor to Jan, who will deal with specific products. Thanks for your interest.
Thank you, Tomas, for your excellent presentation. Before I give the floor to Jan, just a reminder to you as participants, please, if you have any question to Tomas, please put them in the question box and we will handle them after the presentations are finished. Okay, and now I give the floor to Jan.
Thank you very much for giving me a floor. So I'm going to continue with a description of specific products, informal settlements and green areas. I will start with informal settlements. As you probably know, there are multiple definitions of informal settlements or slums, but one of the most commonly used is one from United Nations Habitat, which characterizes slums as an areas with deprived access to basic services such as sanitation, water supply, electricity, accessibility, overcrowding. There is a high density of population and buildings with very narrow spacing between them, substandard housing standards, which are associated with the dilapidated structures and for instance, with localization in areas which are prone to hazards, and insecure land tenure. Insecure land tenure is somehow linked to definition or to the term of formality or informality. It's worth to mention that some areas which might be supposed to be secured in terms of land tenure still can possess some attributes related to deprivation and vice versa. So the things are not black and white. World Bank definition highlights in relation with slums a high concentration of poor people living in substandard conditions. Nowadays, it's been 15 to 17 years when remote sensing has proven itself as a really useful tool to derive some of the above characteristics. It's quite clear that only those characteristics that are visible from imagery can be derived, but other characteristics can be derived using some proxy variables derived from satellite imagery. I'm not going to go deeply into details of mapping methodology, but I would like to stress the fact that before we start with the mapping, we need to proceed with so-called translation of local slum characteristics, which refer to object, settlement, and environmental properties of the slums, into image features or indicators which are referring to detectable properties that are visible from the imagery. They are represented by spectral, textural, geometrical, and other contextual features. And as documented in the images below, it's quite obvious that these features may significantly vary across different countries, continents, between cities, and even within cities where different slum typologies can be found. And to do this definition properly, we need to involve local expertise into this process. Having this, we can delineate the slums, and we use various means, various techniques, spanning from image interpretation, object-based image classification, machine learnings, and in most cases, combination of the above methods that are applied on very high resolution optical multispectral imagery. Very important steps is the open data mining. We use OpenStreetMap to derive certain features, certain intelligence, which is hidden within these layers. And we can also use hazard mapping or modeling using ancillary data or additional satellite data to estimate the hazard and the risk levels and to provide additional attributes. This is an example of slum extent. Being a part of standard product portfolio, it provides information about size, location, and spatial extent of the slums as a polygonal representation. The examples below show from Wanza and Karachi show the option when the slums or slum extent corresponds spatially to the road skeleton, as mentioned by Tomas, to so-called homogeneous urban patches, because these road skeletons usually are enclosing homogeneous built-up textures and densities. The image on the right from Dhaka shows that this is not sufficient enough in some cases. For instance, in Dhaka, there are a lot of pocket slums, so we need to go further more into detail to delineate the slum extent properly. Each of these polygons can be optionally associated or substituted by additional attributes derived by GIS analysis or object-based image analysis. These attributes are referring to slum indicators derived or based on the characteristics mentioned before. They describe the morphology of the slum, dwelling characteristics like mean size, mean spacing, height of the buildings, their orientation, prevailing orientation. They can refer to environment or surroundings, what is the prevailing land use or majority land use, what is the homogeneity, entropy, or heterogeneity of these variables. It can refer to locational attributes derived from distance, from central business district, from various amenities. We can quantify accessibility measures represented by road density, connectivity of roads being referred by distance, by density of some nodes, distance to railway station, etc. And of course, we can provide information about vulnerability to various natural, industrial, or any other kind of hazards that are detectable or derivable by GIS analysis. The advantage of this multivariate attribute approach is that we can provide the user with custom nomenclature. This nomenclature can be derived from one or multiple attributes. Example on the left from Karachi shows the example, the case when we derived the nomenclature from one attribute, from dwelling density, and the example on the right hand shows case from Dhaka, where we used the rule-based classification to derive 6 classes typology based on multiple attributes like soil ceiling density, built-up proportion, distance to railways, rivers, proportion of green, and others. Furthermore, we can monitor the slum evolution using 2 or more satellite imagery. By this way, we can define additional attributes like estimation of slum or dwellings age, and by overlay between the results from different points in time, we can calculate net increase or decrease of the slum area in certain for certain analytical unit for certain zone. If we have available the land use land cover product, we can even calculate the structure of land use consumption and formation. It means we can estimate what is the proportion of different classes that were consumed by sprawl of the slum, etc. This is exemplified in the image in the middle, where we can see highlighted by red color the areas of former slum from 2006 that have been transformed into a different land use by new high-rise developments. And similarly, the blue color refers to extension of the slums, usually at the expense of water, agriculture, or natural areas. This is the last slide for describing the slums and their usability. These products that I've introduced in a nutshell are provided to support development activities at various scales, from local to global. Example from local scale is upgrading interventions, evidence-based targeting of these interventions, while the global scale covers monitoring of various indicators like SDG Target 11 or additional city diagnostics like World Bank's Global City Indicators. Each variable can be transferred into a measure that can be aggregated for custom analytical unit, in this case represented, for instance, by administrative units. More details about this are going to be provided in the webinar 3.2. Now I'm going to describe in a nutshell green areas and networks. I will again start with the definition because there are different ones. UN Habitat highlights the public usage of different type of the land, including streets, parks, squares, etc. While there is another definition represented by Urban Atlas, which define green areas and their associated land more from land use point of view. This is important because for the standard product within EO4 SD Urban portfolio, we use this Urban Atlas definition, which introduces two classes: green urban areas and sport and leisure facilities. Of course, there are some inconsistencies, incoherences between these definitions. Urban Atlas doesn't provide, let's say, a comprehensive definition of living streets and open spaces, and on the other hand, some green areas can be, let's say, melted within framework of classes with associated land. It should be also mentioned that the detection of public spaces is quite problematic directly from satellite imagery, and we need to involve additional information. Mapping methodology for urban green areas is more or less or follows more or less similar concept as mapping of slum areas, with difference that we much more use normalized vegetation indexes, and similar to slum areas, we use OpenStreetMap as a source of additional information regarding transportation, points of interest, labels for parks, etc. This is an example of a standard green area product and its typology. It is derived from baseline land use land cover product, following on Urban Atlas definition that I introduced before. So there are two classes, urban greenery and sport and leisure facilities, and their size, location, extent are provided by this product. If we overlay products from two different points in time, we get the changes, and we can estimate their distribution within area of interest. We can calculate extension of green, removal of green, and additional statistics. But we can also look at this problematic from, let's say, more detailed point of view. We can estimate evolution of green patterns, for instance, at the level of individual urban block level. So we can estimate if cumulative greenness in certain urban block has increased or decreased between two observed periods. And it gives us a very good overview of what's happening with green areas and say grasslands and trees within the city. Well, in order to address the need for extended nomenclature, which provides more diverse open space typology, the optional product has been introduced by our consortium, and also to exploit the full potential of Earth observation and open data in this area. So we take land use land cover product as a baseline, and we substitute it by results from automatic object-based image analysis, and then we derive some certain amount of low-level indicators, either from imagery or from contextual analysis of detected objects. And using rule-based classification, we are again able to meet to the target typology, which is either defined or which might be defined by the user. This is the last slide for urban green products and their usability. Again, these products support development activities at different contexts, and they can be used within evidence-based interventions that are improving livability in the cities. We can support monitoring of global or city-wise indicators, as documented in the small images at the bottom of the page. These indicators may quantify the amount of green, their proportion of green at the level of individual administrative units. We can quantify connectivity of different urban green areas, their accessibility, define the proportion of people living in accessibility distance to urban areas, and etc. And more details about this are also going to be provided in the follow-up webinar at the end of November. It is all from my side at the moment. I will be happy to answer any questions that you may have. And now I will give the floor to Manuela.
Okay, then the last presentation I will be giving cover three main products. The first one is actually a series of products, but it's all under the term of flooding. So it's flood history, flood hazard, and flood risk products. The second is terrain and infrastructure motion and the related risk. And the third is population distribution, density, and an estimate on this population distribution. Concerning floods, first of all, we are dealing with different types of floods here. There are tidal floods in coastal areas. There are short-term local floods after heavy rainfall, for example. And there are large monsoon floods persisting over a longer period of time. Of course, you can imagine that these different floods have a different simplicity to be mapped by remote sensing. And this brings us already to the second point, that we need to use all available data sources to provide a thorough flood history, not only Earth observation data. So in terms of Earth observation data, of course, we use Sentinel-1 and 2, Landsat, VHR data, also Google Earth, whatever we can get our hands on, we use. But we also use like reports, maps, social media. There's, for example, this Urban Voice, where we get information on floods occurring in specific areas, available maps, etc. Here now I want to show you how this flood history has been done for Phnom Penh with Sentinel-1 data. You can see here the time, and you can see then this is north of Phnom Penh. This is the city, north part of the city of Phnom Penh. And in blue, you see the water. As the monsoon flood comes in, this area gets flooded, and then the water recedes again. And if you look at this, like how many observations of standing waters you have, you can have a kind of flood history. If you do it over a longer period of time, you can even get more information on that. This is the flood history, and then based on this flood history, we can map flood hazard. Flood hazard is mapped into 3 hazard classes, because it does not only take into account the flood history, but also like terrain information and, as I said before, reports, maps, whatever we can find, into 3 hazard classes. The third product is the flood risk. Risk is not only hazard, but it's a combination of the probability, which is the hazard, and the consequences. And these consequences or damage is derived from the land use information, which has been explained to you by Tomas. So like the residential areas, industrial areas, the road network, etc. How does that look like? I will not go into very much detail how we derive this. This is this evaluation table, but just give you an example. So let's assume we have an area of forest, and aside of this an area of high density residential area where many people live. So depending on this land use, we have different damages. So for example, in a forest, the damage class is relatively low, while for these high density urban areas, it is high. If we have the same flood hazard, let's say a medium hazard, the damage cost for forest is low, so it gets a lower code, let's say, and on, for example, on the urban high density residential areas, it gets a higher, and that defines our risk classification. So that means that, of course, in the forest, the risk is lower, or it's a low risk, while in the residential areas, it's a high risk. So how does that look like? Maybe it's easier to understand if we look at the map. This is a hazard map for the city of Semarang, northern coast of Java in Indonesia. And you can see that there's, for example, in this area, there is a high hazard. So there's a high probability of flooding. But if we look at the risk map, the risk is medium. That's maybe because this is an agricultural area or something like that, that does not have a huge damage. So this kind of risk map is then, let's say, our main product in this flooding part. Based on that, of course, we can do some statistical analysis. So this is an example. If we have these residential and public urban areas, we can calculate what percentage of these areas is at no risk, medium, at high, very high risk. Similar examples are here shown for Phnom Penh and for Denpasar in the same way. And you can also see that in Phnom Penh we have these monsoon floods very common, so the larger areas are concerned, while in Denpasar there are mainly these flash floods along the rivers, so this is that the pattern looks quite different. Another product which is closely related, at least in some areas, to flooding is the terrain and infrastructure motion product. This terrain and infrastructure motion, or land sinking, we can also say, or subsidence, that's another word, occurs when there is a geological precondition in combination with like groundwater extraction and also with building activities which adds weight to the surface, and then this land is sinking. This is an example again in Semarang, and you can see in this area agriculture has been done in 2003, and this area is sinking, and let's say the sea is eating up all these areas because of sinking, and you can see this here. We can map this sinking, although it's can be only a few centimeters per year, but we can map this from remote sensing by using an interferometric processing chain. And this specific workflow is called small baseline subset method, and it involves radar data. And if you're interested in the basics of radar, please go back on our webinar 2.2, where the whole radar background is explained in more detail. Just very quickly, the main steps: we import the data. We have a crucial step of data co-registration, which has to be very exact in order to map these small changes in the height. Then we calculate the interferograms. We do some coherence and thresholding. Coherence means that we can only calculate this sinking for areas which did not change otherwise. So if we have let's say an agricultural area where there is different crops in different times, we cannot use this part. So for urban areas where the houses are usually stable, we can do that quite well. And then we can calculate this sinking or displacement calculation. If you have any more interest in the background details, there is some references for your further reading. Now an example. This is the terrain motion calculated from Sentinel-1 data for Semarang between December 2014 and March 2017. And we recalculated the whole sinking to average annual subsidence rates, as you can see in this legend here. And we have 4, let's say, sub-products. We have pointwise raw terrain motion products. So for these individual products, we got one of these results. Then we can interpolate that to an area-wise product. So we have an area here, for example, the yellow part is between 6 and 8 centimeters of subsidence per year. Then we can combine that with infrastructure. So we can calculate how many kilometers of road network or of railroad is affected by the different subsidence rates, for example. Similarly, also for different land use classes. And then we can also take statistics out of this. So we can say, okay, so that many percentage or areas in square kilometers are affected of a specific class by this terrain motion. And of course, in the specific area of Semarang, we also use the terrain motion as part of the hazard classification for the flooding. So that went as in a combination into the flood risk product. Now the last product I will explain is the population distribution estimate, which has been done by GAF. The background is that basically there is no information available usually other than census data on an administrative level, or some rough gridded data, world population at 100-meter resolution for specific years. So what we want to have is this population distribution which is needed for example, for the, monitoring different sustainable development goals, or also when we think back now on the flooding or the terrain motion for disaster response planning. So the population distribution estimate depicts the location of people, an estimated population in a specific unit, and the changes over the years if you do that for several years. So what do we have as input data? We use the land use and land cover baseline product that answers us where do most people live. So we can get that from the land use data. Then the population census data per administrative boundary, but administrative unit. So how many people live there in these specific areas. And then we use the soil sealing and imperviousness, which have been introduced also by Tomas before. And this should answer the question on how other people spread in this area. And this is under the assumption that higher soil sealing means more people live there. I have I give you this example. So more houses means a higher soil sealing, while when you have open areas or forests, usually there are less people. The methodology, I will go through it step by step. So first is to project the population data based on the census to the target year. So for example, we have census data from 2012, but our target year is 2015. So we have to project that. The second step is to calculate the average soil sealing per polygon for this area, and then extrapolate the count of people living in each of the spatial units, using this average soil sealing to have an information on how many people live there per soil sealing pixel, let's say. And then these areas are summed up of all the polygons, and this is not the same as the previous census because of the calculations and the equations. So we find a difference between these aggregated spatially distributed figures and the original and correct, let's say, figure. So that makes this last step necessary to adjust these residuals proportionally to the size of the polygons and the soil sealing. Again, if you are interested in the background, there are some references for you to use for further reading. And I will just show you the example how this looks like. So this is an example from Arusha in Tanzania, where you see how the urban population is distribution is in some specific areas. And again, I want to stress the fact that this is an estimate. So of course, in overall, it's correct, but of course there can be differences because of these assumptions in soil sealing and etc. But it is nevertheless a very nice product to do some estimates on spatial distribution of the population. And with that, I'm also already at the end of my presentation. Thank you and goodbye.